Hello everyone, this is AB Calculus section 8.2, day number 1 on differential equations. So as a class opener, what we'd like you to think about is what does it mean to solve an equation and what is a solution to an equation? So how do you prove that a number is a solution to an equation? So for example, let's take a very basic equation. Let's say 40 equals 2x plus 20. There's an equation, and if I wanted to solve it, I would be finding the solution that satisfies that given equation. So for example, I'd subtract 20 and divide by 2, and I'd see that x equals 10. Now that's pretty basic algebra in order to find a solution to an equation. But what that solution, 10, does is it satisfies the equation that's present. What we're going to be doing in this lesson is going to be finding a solution to what's called a differential equation. Okay, this is called a differential equation because there is a derivative involved. Okay, for example, here I've got dy dx. This is called a first order differential equation. First order differential equation. The reason it's called a first order differential equation is because the highest derivative present is the first derivative. Now what we're going to be doing in this lesson is a number of different things. We're going to be using algebraic techniques to find the solution to the differential equation. So for this example, our solution would be a function. So in differential equations, solutions are typically functions. Whereas over here, our solution was a value. I suppose 10 is a function, but it's a very basic constant function. But we're going to be coming up with functions that are not constant as solutions. Now, in some cases, we may have differential equations that are not solvable with the techniques that we have available to us. So algebraic techniques do not apply to solving a differential equation. That's when we'll use what's called a slope field to visualize what's called a family of solutions to a differential equation. We'll see what that is here in a few minutes. Okay, by definition, a differential equation is an equation involving a derivative. The order of a differential equation is the order of the highest derivative involved. We'll be dealing specifically with first order and maybe the occasional second order differential equation. Okay, so let's take example 1 and example 2 and find an algebraic method to find the solution to a differential equation. So we've actually seen some of this before. Okay, it says find all functions y that satisfy dy dx equals secant squared x plus 2x plus 5. So what I'm seeking is a solution y, and actually I'm seeking what's called a general solution. Okay, a general solution, for lack of a better term, produces, right, a family of solutions. Okay, so let's take a look at this. Okay, so if dy dx is equal to secant squared x plus 2x plus 5, if I multiply both sides by dx, what I'm doing in this process is I have now separated variables. Okay, I have all variables y on the left. I have all variables x on the right. This is called a separable differential equation. And when a differential equation is separable, we like that. We can use algebraic techniques. Now with any equation, when I integrate both sides, okay, provided I have dy with a function in terms of y on the left and dx and a function in terms of x on the right. Now you might ask yourself, well, what function of y do you have on the right? Well, I have 1. That is a function of y. Okay, I can integrate and the equation will still be equal. Okay, so the integral of 1 dy is y plus c1. The integral of secant squared x plus 2x plus 5 dx will be tangent of x plus x squared plus 5x plus, I'm going to call this c2. Now from now on, I'm actually not going to write the c1 on the left side. I'm just going to combine and consolidate my constant of integration on that right side. And when I subtract a c1 from a c2, I just get another constant. I'm going to call it c. This right here is the general solution to our differential equation. It has created a family of functions or solutions that satisfy the differential equation above. So if I were to take the derivative of this function, c would drop off and I would get dy dx. Now the reason this is a family of functions is because c could be any value, any real number. It doesn't matter, right? It would just be whatever this function looks like shifted to wherever c is, given, x equals 0. So this is what we typically refer to as an initial condition. And we could find c by plugging 0 in for x, and c would equal y. All right, so we're going to look at going from a general solution, like we did here in example 1, to a particular solution in example number 2. So if the general solution to a first order differential equation is continuous, the only additional information we need to find the value of the particular solution, or the function at a single point, is called the initial condition. Okay, a differential equation with an initial condition is called an initial value problem. So from time to time you may be asked, solve the initial value problem. If it has a unique solution, it's called the particular solution to the differential equation. Sometimes there aren't unique solutions to these, and you'll see those pop up here and there, and we'll get through one in the next set of notes. So let's solve the initial value problem below. So now notice that I'm going to find the particular solution to this differential equation, given that the solution passes through the point 1, 0. So we'll use 1, 0 here in just a minute. So I'm going to separate my variables. I'm going to then integrate both sides. The left side I'll get y. The right side I'll get e to the x minus 2x cubed plus c. At this point, if I was asked for a general solution, I would be done. But I'm not, so I'm going to use my condition 1, 0. I'm going to plug a 1 in for x and a 0 in for y. That gives me that 0 is equal to e to the first minus 2 times 1 cubed plus c. My goal here is to solve for c, plug it back into the general solution to find my particular solution. Okay, so it looks like 0 is equal to e minus 2 plus c. Therefore, c is equal to 2 minus e. Thus, our particular solution in this differential equation would be e to the x minus 2x cubed plus 2 minus e. And there you have it. That is our particular solution to that differential equation. All right, let's continue. All right, so at the very top of the page, you can see what says, what about dy dx equals x plus y? In this particular situation, we don't have algebraic techniques, okay, in order to solve this, this problem. This is considered not separable, okay? The key item here, which makes it not separable, is the plus here, right? If we had dy dx equals x times y, I could separate my variables and keep them in a standard form. If I separated them, I would get 1 over y dy is equal to x dx. We've seen and can integrate both sides of that, but I can't integrate when I separate these variables. If I subtract y, I would get dy minus y is equal to x dx, right? And this right here, that's a no-go, right? We want a function of y times dy. And I can't get that when I use addition or subtraction. So that is not a separable differential equation. So how do we deal with that? Well, what we end up doing is we have a procedure we can use to remedy this, and it's called sketching a slope field. Now, sketching a slope field, in essence, is sketching the solution or a family of solutions to the differential equation. So let's go ahead and let's construct a slope field below. I'll show you a couple of interesting techniques to make you move along a little quicker. It says construct a slope field for the differential equation dy dx equals x plus y, and sketch a graph of the particular solution that passes through the point 2, 0. Okay, not 2.0, 2, 0. Okay, so I'm going to go the slow way here, and I'm just going to I'm going to plot these 9 little slopes right here. Okay, and I'm going to show you a more interesting way to do this. Okay, so let's plot those slopes. This is a slope generating function. If I take any xy, let's take, for example, this one right here. That's the point 3, 3. Then dy dx at the point 3, 3, right, is going to be equal to 3 plus 3, which would be 6. So if I drew a little slope that looked like it had a slope of 6, okay, that looks like kind of like a slope of 6, right? Okay, and I need to do that for all of these points. Okay, let's just do one more, and then I'm going to show you a nice sneaky little trick. It's called an isocline or a nullcline. Okay, that's the point 3, 2. So dy dx at the point 3, 2, and I should have put that same notation above here. Okay, dy dx at 3, 3, dy dx at 3, 2. Clearly the dy dx at 3, 2 would be 3 plus 2, which is 5. Okay, so I make it a little shallower than the previous one. I'm making slopes of 5. Now I'm actually going to write dy dx at the point 2, 3 as well, which would be this point, which should also be 5. Okay, so really what I'm doing is I'm sketching a bunch of little miniature slope lines, right? Tangent lines at each of these points. Okay, so instead of like doing all this mental math, what you can do is you can use what's called an isocline. Here's an isocline. Okay, so let's take our differential equation and let's find where dy dx equals 1. Okay, so what did I do there? I substituted in a 1 for dy dx. Okay, so where does that take place? That takes place if I subtract an x. Oops. If I solve for y, right, then y would equal negative x plus 1. So along the line, negative x plus 1, I get a slope of of 1. Okay, so let's see that take form. So where is the line negative x plus 1? Well, here's the line negative x plus 1. On every point there, along that line, dy dx will equal 1. So boom, 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 boom. Okay, let's use that same idea and find where dy dx equals 2. Okay, well that would be when y equals negative x plus 2. How about when dy dx equals 3? That would be along the line where y equals negative x plus 3, and so on and so forth. Okay, so let's take and let's plot each of these isoclines. So when y equals negative x plus 2, well, here's the line negative x plus 2. I know each of the slopes there will be 2. So I can kind of sketch and imagine each of these slopes of 2. Well, you can kind of catch on to what's going on here. Okay, along the line negative x plus 3, we would have slopes of 3. Okay, so you can kind of see this taking shape. And then I'd have, let me repeat this, 4s. And then like I already have in blue here, 5s. and then in red, 6. And you can imagine, right, kind of formulating all of these slopes, okay, using this idea of an isocline. Now, an isocline is setting dy dx equal to anything other than 0. A nullcline, and you really don't need to know the name of this, but it's just a technique that's useful, is setting this equal to 0, right? Null 0. So that's going to be true when y equals negative x. Okay, so at y equals negative x, all right, let me go ahead and get a different color there. There's purplish. Negative x, I'd get a 0. Right along this nullcline right here, I'd have slopes of 0. Okay, so what you can anticipate is this, is that you can kind of see that I'm going from a negative 6 to a negative 5, negative 4, negative 3, negative 2, negative 1, 0. Then I should have negative 1s. Okay, so then you can see that I'm going to have this slant asymptote here, then a negative 2. Now, not every slope field works like this. Negative 3, negative 4, negative 5, and negative 6. So you can see this cool slope field taking shape. Now let me sketch the particular solution, right, that goes through the point 2, 0. So where's 2, 0? Here's 2, 0. That's the point 2, 0. So if I were to sketch the solution, I think the solution would look something like this. Right, kind of hit that slant asymptote. This would be the particular solution through the point 2, 0. Okay, so you can see that clearly, you know, if I had a solution down, or excuse me, a solution that passed through this point here, which would be, what is that, negative 1, negative 3, that's going to look a whole lot different than a particular solution above that slant asymptote, right? Now that is the technique using isoclines and nullclines. And of course you can do calculations all day. You can do them all day on this curve and potentially screw up the algebra. Or you can use this idea of an isocline or a nullcline. The isocline and nullcline are useful typically with, you know, expressions like this, x plus y. But there are some differential equations that aren't quite so nice to work with. Let's look at a few. Okay, so reading a slope field, a few features that are easy to identify and help sort out some problems. Look for places where the slopes are 0. That's a nullcline. Right, so this is a nullcline. Look at slopes along the x-axis. Okay, so that would be, in particular, let me see if I can change my colors back here. Here we go. This would be, right, where y equals 0. Or along the y-axis, this would be where x equals 0. Look to see if slopes depend on just x or y, and look to see where slopes are positive and where they are negative. And really, I'd add in here, use a nullcline, which we talked about in the first bullet point, and an isocline, if necessary. Okay, let's continue to the next slide. Okay, which of the following slope fields, or is the slope field for the differential equation dy dx equals x over y? Now this is, I mean, honestly, this is a classic isocline problem, okay? You could look all day at like determining, well, let me go to 5, 5. Well, 5, 5, right? Wouldn't dy dx at the point 5, 5 equal 1, right? Just 5 over 5. Okay, well, I guess you could do that, and you could eliminate almost every one of these. Or what you could do is you could just say, hey, I want to know where dy dx equals 1. Well, if dy dx equals 1, then that means x over y equals 1, which means that this isocline, y equals x, will represent, okay, anywhere that y equals x will represent a slope of 1. Okay, so let's go ahead and take a look. Okay, as I look on the curve, any one of these curves, here's the line y equals x. Okay, here's the line y equals x. Here's the line y equals x. And here's the line y equals x. And then, of course, the last one. Okay, so, I mean, I just basically look at each of the graphs. Do the slopes on the slope field match up with a slope of 1 here? And the answer to A is no. right? I can see clearly these little slopes here are not 1. Okay, based on the square representation of quadrant 1 there. Okay, part B almost looks like it could be, but it looks like it's shifted down a few units, so that's out. Part C clearly out, and part D clearly out. So I used the isocline, right? Where did dy dx equal 1? And I could do the same to kind of show that, right, if dy dx equals -1, then that means that -1 equals x over y, which means that y equals -x. So along the line y equals -x, I should have a slope of -1, which, there you go, there's your confirmation. So isocline was really nice in that particular case. Let's continue to another example. Okay, let's go the other way a little bit and find the solution to this differential equation, right, based on the slope field. Okay, so I want to look at the slope field, and one thing that I can do is, let's take a point. Let's just pick a value. Okay, let me pick this value right here, and I don't know what that value is. It kind of looks like 1, 0, right? And let's sketch what would be the particular solution to that differential equation that passes through the point 1, 0. Well, it kind of looks like it would take on a form kind of like that, right? Well, based on the form of that graph, I mean, x squared clearly does not represent that. E to the x, that's out, right? E to the x kind of looks like this with a horizontal asymptote as we head to -infinity. So that's out. E to the -x is a horizontal reflection of that same graph, right? With a horizontal asymptote as x heads toward positive infinity. And clearly that's not cosine x. So our answer here in this particular case would be the natural log of x. Okay, so our particular solution to that differential equation would be natural log of x. So let's take another possible value, right? Let's take this value here, and I don't know what that is, but eventually the curve would take on a very similar shape, right? You can see how this is the natural log function potentially just shifted horizontally and vertically. So this would be another particular solution. I don't know what this would be, but this would be natural log of x, let's say, plus some value c. Okay. Now, I do want to talk about an alternative method or strategy to visualizing these differential equations. If that made sense, go ahead and fast forward, move down to example 6. Okay, just kind of fast forward and don't listen to me. This is another way to kind of look at solving this particular differential equation. Okay, so what I'm going to think of this graph as, I'm going to think of this graph as dy dx. All right, and if I look at the graph as x approaches 0 from the right, so the limit as x approaches 0 from the right of this function dy dx, it looks like it's headed toward infinity, right? Look at these slopes. They're kind of headed toward vertical slopes, right? Which are slopes that do not exist. Okay, and then if I look out on the right end, right, it kind of looks like these slopes are headed towards 0. They're trending to 0. Okay, so the limit as x approaches positive infinity of dy dx looks to be headed towards 0. Okay, so if I were to look at my 5 options and I were to take the derivative of each of them, this would equal y prime. Y prime in the second case would be e to the x. Y prime in the third case would be negative e to the negative x. Y prime in the fourth case would be negative sine x. And y prime in the fifth case would be 1 over x. Okay, which of those functions, as x heads to 0 from the right, heads to positive infinity? Well, this is wrong, right? As x heads to 0 from the right, that heads to 0. This is not going to work. That's heading toward 1. This will not work either. Negative sine x, I suppose that's a possibility. And then 1 over x, that's a possibility. Now let's look at the other side of things. The limit as x approaches 0, x approaches infinity of dy dx. So as x approaches infinity of y prime here, we don't really know, right? We don't really know what that's going to look. That doesn't approach anything as x approaches infinity, it oscillates. So that's out. But I do know that the limit as x approaches infinity of 1 over x, that equals 0. And there you go. I've now confirmed that y prime equals 1 over x. Well, if dy dx equals 1 over x, and I separate my variables, 1 over x dx, and I integrate, I get y equals the natural log of the absolute value of x plus c. And so I'm not going to go much further with that right now because it's kind of loaded with the absolute value. But there clearly we have confirmed going the other way that the solution to this differential equation would be natural log of x. All right, let's go down to one more example, example 6 here, and then we'll call it a day. I think that's it for this note set. Matching slope fields with differential equations. You can pause the video. I'm going to go through a couple null-cline, isocline options here and match these up. So use slope analysis to match each of the following differential equations with one of the slope fields. Do not use your graphing calculator. Okay, match the slope fields with their differential equations. So as I look at A, right, as I look at A, I think, hey, look at that. I like this null-cline here. Okay, so what I'm going to do is I'm going to set each of these equal to 0 and solve and see if any of them come out to be a horizontal line. So let's go ahead and look. I'll set the first equal to 0. Well, where is sine x equal to 0? That's not necessarily something I want to look at. So I'm going to skip that for now, but I'm going to go to 8. All right, I'm going to look at this. Where would this be equal to 0? This differential equation would be equal to 0 at y equals x. Well, this line up here, that's not the line y equals x. Okay, so I'm going to do a little work with that in a minute. Okay, how about number 9? If I set that equal to 0, finding the null-cline would be y equals 2. Hey, that looks like it matches up. Right, wouldn't this be the line y equals 2? I don't know why I put 2 equal sign there, but it's all good. So I'm going to say that this is the differential equation, dy dx, 2 minus y. Okay, let's look at, again, let's set this last differential equation equal to 0, finding the null-cline. Hey, cool, that's equal to 0 whenever x is equal to 0. Well, that's cool. That kind of lines up nicely right here. Right, I see slopes of 0 when x equals 0. Therefore, this would be the differential equation, or the slope field for the differential equation, dy dx equals x. Cool. Let's go ahead and look at part C and part D. And I skipped number 7 here when I looked at the null-cline right away because I didn't really feel great about that, right? At least based on the traditional methods of using the null-cline. But I know that this would be true anywhere that x equals 0 plus or minus, okay, pi units. So that would be at x equals 0, at x equals pi, at x equals 2 pi, and so on. Well, I see x equals 0 here. This is kind of weird and goofy, but this would be x equals pi, and we would see that pattern continue every pi units in both directions. That's cool. This slope field represents dy dx equals sine x. Very good. And then the last one, of course, I haven't matched up which one yet. I don't even know. Oh, number 8. I haven't matched that one up yet. This would be 0, right? The slope or the null-cline would be located when y equals x. Well, look at y equals x here. Look at the slopes along there. All I had to use, you guys, in order to find and match these slope fields up with their differential equations was to use this idea of the null line. There are many, many other ways to do this. Okay, many others, but this is just one. All right, that's it for this lesson on 8.2. We'll see you in the next video.